Now, we've seen these sorts of arguments before. What we're doing is we've got a point here and we're trying to work out what the gradient of the tangent is at the point x sine x. So what we do is we approximate that with a chord here between x sine x and x plus h, sine x plus h. It should be clear that this distance is h, that's the difference between the x coordinates, and this one here is sine of x plus h. Take away sine x, which is the difference between the y coordinates. So that is the difference in y over the difference in x. Remember, what's going to happen is we're going to shrink h so the points move closer together, and then the chord becomes a very good estimate of the tangent. So delta y over delta x, always with these first principles things, is the f of x plus h, take away the f of x, divided by h. In this case, our function is sine. So what we're going to be doing is we're looking at the differential of y equals sine x. So we've got sine of x plus h, take away sine of x, divided by h. Now we have some expansions which we looked at in year 11 for the sine of a plus b. So sine a plus b is sine a cos b plus cos a sine b. And so this becomes sine x cos h plus cos x sine h minus sine x, all divided by h. Factorizing these two terms here, I get sine x into cos h take 1. And then I've got plus cos x sine h over h. What I'm then going to do is split the fraction. So I've got sine x into cos h take 1 over h plus cos x sine h divided by h. Now we know from previous work that we've done that dy dx is the limit as h tends to 0 of delta y over delta x. Now again, without justifying, if we take the limit of the whole of this, we can split it into separate limits. Well, let's just do that one step at a time. So dy dx is going to be the limit as h tends to 0 of all of this lot. So sine x cos h take 1 over h plus cos x sine h over h. So just as we did with the multiplication before, there is a law of limits that says dy dx is the limit as h tends to 0 of sine x cos h take 1 over h plus the limit as h tends to 0 of cos x sine h over h. So we can split the limits like that. Now, think back to what we've established. The sine x is independent of this. But this bit's going to go to 0. The cos x is independent of this, and this is going to go to 1. Okay, that's just foreshadowing what's coming. So let's just... Sine x is independent of h, so we can bring it outside. So you've got sine x times the limit as h tends to 0 of the cos h take 1 over h. And cos x is independent of h in the second one, and so we can bring that out as well. And then that's multiplied by the limit as h tends to 0 of sine h divided by h. Now, as I mentioned just now, you can see it in yellow above, this limit here is 0, this one here is 1, and so what happens is dy dx just ends up being cos x. So if y is equal to sine x, dy dx is equal to cos x. And using a similar analysis to this, you can show that if y is equal to cos x, dy dx is equal to negative sine x. And what that does is it gives us a cycle, which looks like this. And you can see sine x differentiates to cos x. Differentiate is the blue arrow. Cos x differentiates to negative sine x. And since sine x differentiates to cos x, it follows that negative sine x must go to negative cos x. And then negative cos x goes all the way back round here to sine x. So you end up with a cycle. And because we're coming on to integration next, and it's a reverse process, the same diagram can be used for integration.